Hey there. So today we are going to be looking at the directional derivative of a two variable function, and this thing is like really close to my heart because it answered a question which I had been asking like a million times when I was learning calculus, multivariable calculus to be specific. And basically I derived the formula for a directional derivative in my own way, so it's something which I like a lot. So let's get started. So we know that f prime of x, which is the derivative of f of x, is nothing but the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's like the definition of the derivative. So we can also extend this to a multivariable function. So if we have f of x y and we partially differentiate that with respect to x, so we can write that as the limit as h goes to 0 of f of x plus h comma y minus f of x comma y over h. So in this case we are holding y constant and we are just changing x a little bit, and then we are subtracting the original value and seeing what this limit approaches. So now I'm not going to be writing this limit as h goes to 0 again and again. Whenever I write h anywhere, you have to like know that it's just limit as h goes to 0. So fine, this is all fine. You can take the partial derivative, you can do the same with y, like the thing which we did with x, you can do the same with y. Fair enough. But my question when I was learning multivariable calculus was that what if I change both of them? I mean, it's still a valid limit, I can still evaluate it, and I don't think I'm doing anything illegal. So what if I do f of x plus h comma y plus h minus f of xy over h? I mean, that's completely fine, right? I can still evaluate this limit as h goes to 0. And if you in fact multiply h by cos theta and sin theta here, so if you write it as f of x plus h cos theta comma y plus h sin theta, and then subtract f of xy and divide that by h. In fact, if you take this limit, then it actually has a pretty geometric interpretation. So if you have a 3D function f of xy, so z equals f of xy. So let's say the graph looks something like this. So this is a surface above the xy plane. So what the partial derivative does is it keeps y constant. So this is the x-axis, y-axis, z-axis. So it keeps y constant at a value, and then it changes x. So let's say this was a point x comma y, and then it takes it a bit to the right by x plus h, by h. So this point now becomes x plus h comma y, and then let's say x comma y maps to this point on this surface, and x plus h maps to this point on the surface, and there will be a certain difference in z created. So if I see the z value for both of these points, then this thing is the partial in z, and if I divide that by the partial in x, I get the partial derivative in x, and this is nothing but f of x comma y. So this point, the z coordinate is f of x comma y. So maybe I should write it over here. So this is f of x comma y, this is f of x plus h comma y, and similarly you can also keep x constant and change y. That's also like it's symmetric in x and y basically. So you can do this, but what if we were a bit creative or naughty, whatever you want to call it, and we did something like this. So once again, this is a 3D space xyz, and this is our graph. And let's say instead of keeping either x or y constant, I drew a line, okay, on the xy plane, let's say something like that, which makes an angle theta with the positive direction of the x-axis, so the positive direction. And let's say I take a point x comma y which lies on this line, and it maps somewhere over here, and then I take a tiny step of length h along this line, and then I land up somewhere over here. And this, now what is my new point? Well, I changed x by h cos theta and I changed y by x sin theta. So this length here is h cos theta, and this length here is h sin theta. So my new point is x plus h cos theta and y plus h sin theta. So now I can once again take the projection on the z axis and see what the z values are. So this is f of x plus h cos theta comma y plus h sin theta, and this is f of x comma y, and I can take the difference and divide that by h to get some new kind of derivative. I mean, you can still call it a derivative because you're taking a tiny step and then you're seeing the change in the function, you're dividing it by the change in the function. So this is still some kind of derivative, and this is in fact called the directional derivative. So if I change x by h cos theta and y by h sin theta, and then I divide it by h, then I get the directional derivative. But how do you evaluate this thing? I mean, we know how to evaluate the partial derivatives, so we need to find some method to evaluate this derivative as well. So let's do that. So we have this, we want to evaluate the limit as h goes to 0, and it has the nice interpretation, nice geometric interpretation, that if you draw a plane something like this, which is like perpendicular to this line, then okay, and if you see what the graph looks like along this line, so let's say it looks something like this, then this ratio, this limit, will in fact be the slope of that graph along this plane. So it has that nice interpretation. So if we had taken the partial derivative, then in terms of x, then theta would be 0, and we would be asking what's the slope of this graph along a plane which is perpendicular to the x-axis. And similarly, if you are taking the partial derivative in y, same story. So let's evaluate this limit. Let's see what we can do. So I discovered all of this before learning about the directional derivative. Like, I asked the question, what if I change both the variables at the same time? It's still legal, but what interpretation does it have? How do I evaluate it? I figured it all out myself, and then around a month or two later, I learned about the directional derivative and the formal way to derive it from a Khan Academy video. And I was like, damn, they stole my idea. Okay, so let's get started with evaluating this limit. So we know how to evaluate a limit which looks something like this, but we have no idea what to do when both of them are changing. So maybe we can introduce a term in which relative to this only one term is changing, and relative to this only one term is changing. You'll see what I mean. So we can take, so I won't write the limit thing, f of x plus h cos theta, y plus h sin theta, minus f of x comma y, and now let's add and subtract. So let's subtract f of x plus h cos theta comma y, and let's add the same thing in. So we have f of x plus h cos theta, comma y, and that entire thing into 1 by h. So what I basically have done, I've added and subtracted the same terms, so that doesn't change anything. And we can in fact evaluate this limit, this difference divided by h, and we can also evaluate this, because if you see, the x part is staying constant, it's x plus h cos theta in both cases, but the y part is changing, and here the x part is changing but the y part is the same. So we can use that, and we can use our knowledge about the partial derivative and its formula, and we can evaluate this. So let's split it up. Since we know how to evaluate the difference of these two terms and these two terms, let's break it up into two fractions. So we'll have f of x plus h cos theta, y plus h sin theta, minus f of x plus h cos theta, comma y, and divided by h. So we'll look at this part later. Let's first look at this part. So now our increment unfortunately is h sin theta, but we know how to deal with if it was simply h, like there was no coefficient attached to the x other than 1. So if it was that case, we would know how to deal with it, but here we have an h sin theta, so we don't know how to deal with it. So how about we multiply and divide the entire thing by sin theta. So now I have h sin theta in the denominator and h sin theta as the increment in y, and we know how to evaluate this. So if I say h sin theta is equal to u, then this is u, and since limit of h goes to 0, limit of u also goes to 0, because 0 times sin theta, no matter what theta is, it's still 0. So this is nothing but the partial derivative of f with respect to y evaluated at x equal to h cos theta. So this is sin theta times f sub y. Now f sub y is basically the partial derivative of f with respect to y evaluated at x plus h cos theta, comma y. And in fact we can ignore this, because now we don't have we can just say that since limit of h goes to 0, and assuming that this function is continuous, we can say that f of x plus h cos theta is nothing but f of x. So this is the first part of our answer. We know how to calculate this. We have found that, and let's do the same thing with this difference. So once again, same trick. We have f of x plus h cos theta y minus f of xy and divided by h. So once again, since the increment is h cos theta, but we don't know how to deal with h cos theta, we only know how to deal with h cos theta in both cases or h in both cases. So let's multiply this by h cos theta and multiply on the outside by cos theta, and we know that this is nothing but f sub x of xy, and we have a coefficient of cos theta attached to that. And since our final answer was just the sum of these two differences, we can add those together, and we get that this limit here is in fact cos theta times f sub x xy plus sin theta f sub y xy, and that's the answer. So once again you can ask that what if I didn't have cos theta and sin theta over here? What if I had, let's say, 2 and 3? What would I do in that case? Well, it's pretty easy to show that this is nothing but 2 f of xy f sub x and 3 f sub y xy. And the reason I used cos square and cos theta and sin theta here is because then it keeps the nice interpretation of being the slope of the graph along a plane. But if you have some two numbers, let's say in general k1 and k2, and the square root of k1 square plus k2 square is not equal to 1, then you will lose that nice interpretation of it being a slope, because this will in fact be this factor times the slope. So if the slope is let's say m, so the slope of the graph along that plane is m, so let's say the graph looks something like this, and let's say we are finding the slope at this point. So if this slope was m, then if we and let's say the point, our point is here, x comma y, and let's say you took some multiple of cos theta and some multiple of sin theta, then the same by the same factor, then you would have this thing times m as your directional derivative. But then that derivative would no longer have the nice interpretation of being a slope, and that's why it's not like the initial derivative which Newton thought of. And in fact, some people don't like to have sin theta and cos theta here. They like to have generic k1 and k2 factors, but it's really up to the person. I mean, some people like to have cos theta sin theta, like myself. Some people like to have k1 k2, and some people like to divide the entire thing by square root of k1 square plus k2 square, which is in a way the same thing as cos theta sin theta, just that you have it in a different form. So ultimately it's all the same thing, but some people argue that not dividing by this factor and just keeping it the way it is also has some nice interpretation. So they are right in their own way, I'm right in my own way, so you can have whatever you want. So the directional derivative can either be normalized by dividing by the square root of k1 square plus k2 square, or you can just keep it as it is. It's up to you. Just you need to specify which case you're taking. And now this brings us to another interesting topic. So I'll get rid of this and I'll be right back. Okay, so if you have taken a multivariable calculus class, then you probably have heard about the gradient and how it is the direction of steepest ascent. So let's prove that. So we have that the directional derivative, which is often written as the derivative along a unit vector v hat, or for some people just some arbitrary vector. So I'll prefer v hat because I like the sin theta cos theta version. So this of f of x comma y is nothing but cos theta f sub x of x comma y plus sin theta f sub y of x comma y. And so this basically tells us that v hat is equal to cos theta sin theta, the vector with the components cos theta sin theta. And so we can make up a new vector, and this is called the gradient vector, and it will be the vector. So let's denote it with I don't know, w vector, let's say. So let w vector equal f sub x of x comma y and f sub y of x comma y. So the x component is the partial derivative in x, and the y component is the partial derivative in y. And we can also say that the directional derivative of f of x comma y is nothing but v hat dot w vector, right? Because if we take this dot product, then it's going to be f of f sub x times cos theta plus f sub y times sin theta. The corresponding components multiply. So this is a fair way to say it. And now we can ask the question, when does this product get maximized? So we know that any vector, a vector, let's say, dot b vector is equal to ab cos theta. So maybe I'll use phi because we've already used theta. So a is the magnitude of a vector, b is the magnitude of b vector, and phi is the angle between them. So this tells us that when cos phi is equal to 1, then the dot product of a vector and b vector will be the maximum for any two constant vectors a and b. So when is cos phi equal to 1? Well, that's equal to 1 when phi is equal to 0, like 2n pi, but let's just take 0. So when phi is equal to 0, so that means they are pointing in that same direction. So a vector and b vector can't be something like this, they can only be something like this. So this is a vector and this is b vector. They are pointing in the same direction, they may have different magnitudes, that's out of the question, but basically they have the same direction, so that's when this dot product is maximized. And from there we can say that this dot product is maximized when v hat and w vector are in the same direction. So v hat looks something like this with magnitude 1, and let's say w vector is much longer and it looks something like this, and this is v hat. So when this happens, this dot product is maximized. And what does it mean by, what do we mean by saying that this dot product is maximized? Well, that means that the directional derivative is maximized. And what does that mean? Well, that means that we have basically found the direction in which the slope of the graph is steepest. So if you take a point x comma y in your on your xy plane in the xyz space, wait, I'll draw this better. So let's say this is your point x comma y, and and this is your graph. So now equipped with the directional derivative, you can tell me that if I choose a particular direction of angle theta, then you can tell me the slope along that direction. But if I ask you that in which direction is this slope the maximum, you can now tell me using this knowledge that it's maximum in the direction when these two vectors are pointing in the same direction. And well, w vector is fixed because if you for any given point x comma y, the partial derivative in x is fixed, the partial derivative in y is fixed of a given function f. So we can only change v hat, and what v hat should we put so that this dot product is maximized? Well, v hat should be in the same direction as this vector. So if I make this vector like this, v hat should be pointing in the exact same direction. So in fact, if you take this vector, it will tell you, like the direction of this vector will tell you in which direction is the slope of this graph maximum, and that is what the gradient is. That's why it's called the direction of steepest ascent, because if you go in the direction in which this vector points, then the dot product is going to be the maximum, and the dot product is going to be maximum implies that the directional derivative is going to be maximum, which implies that the slope of the graph in that direction is going to be the maximum. And I hope you like that way of deriving the formula for the directional derivative. And it's a pretty good question. I mean, what if you change both variables at the same time? And you can extend this idea to any number of variable functions. So thanks for watching.